Here. Today is going to be basically, I'm going to go a little bit into networks and subnets that will actually answer the first question, and it will hopefully make it much clearer how the hierarchy works, how IP addresses work. And then we'll go into one small topic of datagrams and virtual circuits, because that's something the syllabus requires me to cover, I guess. I'm going to talk about that, and then I'll go back into the IP header, talk about the IP header fields. And time permitting, I'll look into how we give out addresses in a local area network. So let me start right away with this notion of networks and subnets. By now, you should understand a little bit about the fact that we're trying to solve a problem of scaling. We have very many destinations or hosts, let's say 7 billion, 10 billion, something like that. So everything has to be designed in a way so that we aren't going to be overwhelmed. No router is going to have to deal with this very large number of addresses. So what we're going to do is to make the problem smaller. Okay? At each level, we're going to try and make the problem smaller so that we don't have to deal with the scaling issue. And so more specifically, what we're going to do is that if you take the space of all addresses, so we have 32-bit IP address. This is basically corresponding to 2 to the power 32, approximately 4 billion endpoints. Okay, and we have more than 4 billion endpoints right now because of the fact that we can share addresses using NAT, and we'll come to that in a minute. But still, 4 billion is quite a lot. No router can actually deal with 4 billion addresses. Okay, it's just not possible. You can, but it will be very, very slow. So you don't want to actually do it. So what we're going to do is we're going to use the notion of subnets and networks and geographical allocation of IP addresses to do something called aggregation. Okay. So what I talked about last lecture, I'm going to revisit the same exact thing, but instead of starting from the bottom up by drawing all the addresses and showing how we can combine them to get the low order bits looking the same, I'm now going to take the same exact thing and view it from a different perspective, which will hopefully get you a better idea what's going on. This is what I mean by aggregation. By aggregation, I mean that we can take a set of addresses like A.B.C.D, okay? Let me just say, let's see, 1, A.B.C. or maybe 0, 0, 0, 1, and A.B.C.10, A.B.C.11. Let's say these are 4 addresses, okay? I can refer to all of them as something like A.B.C.0/2, okay? Which means that, sorry, in this case, /30, okay? Which means that the last 2 bits are the only ones that are going to be significant, okay? So this notation down here, A.B.C.0/30, okay? Is it visible from the back of the room what I'm writing at the bottom of the board? Can you guys see it? Yes? No, you can't? Okay, so some of you, the taller people, can see it. The representation I'm writing is A.B.C. 0/30, okay? It looks complicated, but let's just look at it. So we know it's a 32-bit IP address, right? And you're saying that this one, you can read it as ignore. What am I doing here? Oops, sorry. Right, so we want to ignore the, so you want to mask, this is the size of the mask, okay? And so what we're saying is that the length of the mask is this, so we have 30 sections that we're masking out, okay? And what we're masking out means that's the stuff that we're going to actually look at, and everything else we are going to ignore. So the last 2 bits, 32 minus 30, so ignore 32 minus mask, okay? So what that means is that if anybody else wants to refer to all 4, they can ignore the last 2 bits, the 0001, 1011, we can ignore it. Why is that? Because we have some kind of what we call a subnet, and there is some way to get to it with this router R, okay? Now, if all the addresses over here are the form A.B.C.D, or sort 0, whatever, /30, okay? Then from the outside, they can ignore the last 2 bits. It just doesn't really matter what they are. They have to get to here anyhow. Okay? So it doesn't matter what these last two, if it doesn't matter 0, 0, 0, 1, 1, 0, 1, 1, it doesn't matter what they are, we're going to have to give it to this router anyway. Okay? Does that make sense? Okay, let me try with a smaller example over here. Let's say we just have addresses of the form, let's say we have 4 computers, okay, and they're called 0, 0, 0, 1, 1, 0, 1, 1. Let's say we have these 4 computers, and this network is called network 1, and then another network which is called network 2, which also has the same 0, 0, 0, 1, 1, 0, 1, 1, okay? All right. So I claim that I can call all of these 1 dot star and 2 dot star, okay? Does that make sense? Yeah? Now, if I have some router R over here, it has a connection like this over here and connection like that, and it gets a packet of the form 1.10, for example, okay? Over here, the routing table, all it has to say is that this is port 1, this is port 2. All the table it says is 1 dot star, send it to port 1, 2 dot star, send it to port 2. Is that clear? Right? So by aggregating all these addresses together, what I'm saying is ignore the last 2 bits, or ignore everything that comes after the dot. Right? Is that clear? So if I get a packet that says like 2.01, I ignore the last 2 bits because that's what it says in the table, and I look up the port, it's 2, and off it goes over there. I don't need to know that there's the 0, 1. I don't really care what it is. I just ignore it. Right? Yeah?
So this system makes perfect sense. I get confused when you go from this to the slash.
Yeah, I'll come to that. This system makes sense, right? Okay. Now, when I say that, when I talk about this, so let's be clear. I can't use actually 2. I've got to use over here. I've got to use 0, 1, and then 1, 0, right? Because that's 2 is not a number we can use, so it's 1, 0, right? And this is 0, 1. And this has got to be network 0, 1 dot star. This has got to be network 1, 0 dot star. Okay? Now I made that change, and I call this network 1, which is equal to 0, 1. This is equal to 1, 0. I haven't changed anything other than relabeling 1 as 0, 1 and 2 as 1, 0. Does this still make sense, Tommy? Yeah? Everybody with me so far? Yeah?
So 1 is 0, 1, so where is 0, 1, 0?
Beg your pardon, this one? Oh, this one is a destination address of the form 10.01. So there's a network called 0, 1, and then inside is a host called 10, this one right here. So the address of this would be called 10 dot, sorry. So this would be 10.01, this is 10.10, for example.
Oh, so it's switched around?
No, so this is the network number followed by the host number. Just like an IP address, we have the first part is the network number, and then the second part is the host number. Yeah? Oops, sorry. Oh. Thank you. I wasn't paying attention. Thank you. Yeah. This one would be 10.01, and this would be 10.11. Yes, sorry about that. Yeah. Okay.
Is that still right?
This is correct. These are just 2 packets that came in. One with the destination 10.01, the other one called 10. So 10.01 is going to go here, and then 01.10 is going to go there. Okay. Make sense? Okay. So this example should hopefully illustrate the power of being able to refer to everything in this space with just one thing, which is the star over here, 0, 1 dot star. Okay? So everybody fine with the star? Okay, because if you don't understand this, then there's no point in moving on. So I want to make sure everybody gets this. Okay. So I can summarize this by saying that by taking all these addresses and aggregating them up in this way, I can refer to all of them in one single way, like this. Instead of having a routing table that spells it all out, I got it. Instead of saying 01.01, 0.10, all the way over, instead of having 4 entries, I just got 1. But imagine over here, instead of this, I had 2 to the power 16 addresses. I would need 2 to the power 16 entries, but I can collapse them all down into just 1 entry by using this over here. Okay? All right. Now let's go to the slash notation, which is confusing, I have to say. Yeah.
So in order to have 1 entry, you need to
You-
mask is.
Correct. I'll come to the masking in a minute.
Okay.
Okay, I'm going to come to masking in just 1 minute, so hold on that. All I'm saying is that I'm referring to the aggregate using a single entry. That's all I'm saying, right? Because I want to focus on aggregation over here.
Yeah, I'm just confused because at first you said you're going in the routing table for that battery, you're going to have the anyways, so, and now you're saying you need that.
No, I don't need to have individual entries for each host. I just need one entry for the aggregate. That's all I'm saying.
Yeah,
Okay.
so,
So,
I don't know how to explain it. Maybe it'll become clear.
okay, so if you have a question, maybe after class you can anybody else? Clarence, you had a question, yeah.
So going from the problem we have there, which is there's only 4 billion addresses,
Right.
they still seem to be unique. Like, I'm not getting.
Over here, they're still unique, correct. I've not done anything else. We'll talk about NAT later on, which makes them non-unique and so on. But at this point, they're all unique, correct.
Okay.
Yeah. Any other questions about this? Okay. So I'm going to keep this picture as it is. I'm going to just change one more thing in the notation. So when I have one dot star, 2 dot star, everybody's okay, right? Okay. All right. This is fine. Okay. Now I'm going to I'm going to take this. I'm going to show you what a mask is. I think maybe you guys have not seen this before. So let me explain something about what a mask is. Let's say I have a bit string of the form 1011011011, 10110111. Let's say I have this. Okay, this is a bit string. Okay, and what I do is that I write down a bit string like this 11110000. Okay, and what I do is I say do the bitwise AND of these two. Okay, what does AND mean? They both have to be 1, otherwise it's a 0. Okay, that's what AND means. So if I do this, what happens? Well, these are definitely going to be zeros. And here it's going to be a 1 if the top one has a 1. So it's going to be 1011. Right? Does everybody get that? That's sort of, hopefully you've seen this in some first year class or something like that. That's a bitwise AND. We call this, we call this the mask. Okay? And you can view the mask as a selector. So select, we can say select the top, in this case, 4 bits. Okay? And that's what we call a bit mask. Everybody okay with that? Select the top 4 bits as a mask like that. How do I say select the top 8 bits? It will be a mask like this. Okay, in this case, it will be 1111, 1111. That's select the top 8 bits. On 7 bits, it will be this. It will be select the top 7 bits. It's going to be this one, right? So it's just a number of ones in the mask tells me how many bits I'm selecting. Okay? Everybody okay with that? Okay. So I have to somehow represent the star over here. I got to say 01 dot star. You know, what the heck does star mean? It's no, star is not a symbol you can use. Okay? So what we do is that we say, okay, let's assume that this field is 4 bits and this field is 4 bits, exactly as I have over here. I have 4 bits over here, I have 4 bits over there. Okay? What I want to say is, I don't really care what the last 4 bits are. I just care about the first 4 bits. Okay? Remember, to do that, select the top 4 bits. Just select the top 4 bits and make a decision. That's what I want to say. How do I do that? I say use a mask of length 4. Okay? So I'll say use the mask 11110000, and here use the same mask 11110000. Okay? Does that make sense? So I'm saying take the destination IP address that I got, AND it with this mask over here. I'll get some number. If that number matches this one over here, which is 01.0, then everything is fine. I got a match, otherwise I don't have a match. Okay? That's fine. And we call this, this notation is /4 is what we would call it. So that's a /4 mask. Okay? So this one would be what's called a /7 mask. You're going to mask the. So the longer the mask, the more the bits there are in what corresponds to the network. Yes?
So you send the IP address and you send the mask.
We don't send the mask. The mask is in the routing table. Okay? Mask is in the routing table. I'll come to your question in just a minute. We'll do a small example. You'll see what's going on. Okay? Yes?
Why don't we just shift right instead?
Okay, because we have to tell how many steps to shift right. And that's exactly the same as specifying a mask. just a way, just a convention how to represent it. But yeah, it means the same thing pretty much. Yes?
Sorry, where did you get the 1110 from?
Beg your pardon, this one?
No, the second part of it. Yeah.
Oh, I'm saying all of this together is a 8-bit string, right? Because I'm doing 8-bit strings and have 4 bits here. I'm considering 8-bit strings. If I were to consider 8-bit strings, well, I just want to represent, I just made it up. I just said, what would a mask of length 7 look like? I would call it a /7. It would look like this. What's a mask of length 3 look like? It would look like this, 1, 1, 1, 0, 0, 0, 0, 0, and call that a /3. Okay, that's the meaning of that. Okay, everybody fine with that? So now we know how to represent star. What we do is we take the all these addresses over here, 01.star. We'd say, okay, I'm going to have the first 4 bits represent the network number, which is the network that's shared by all of these. And these guys are going to be the things we don't really care about in looking up. So this will be a /4, for example. Okay? Now, this is using 8-bit strings. If I had a 32-bit string, 32-bit string is what we would use in IP. It looks pretty much the same, right? In 32-bit string, I want to say how many leading ones do we want to have. So let's say I have an IP address. Okay, so I'm going to now go back to this one. And that's what I was going to draw over there. So let's take address 129.97.24.2. Let's say that's the address I have over here. Okay, and let's say there's a subnet, like so, where all the addresses start with 129.97.24, and then here it's 129, for example, .97.24.1, 129.97.24.7, whatever. There's some other numbers, but they're all starting with this, so it's .star, right? That's what I have. They all are starting with the same prefix, and the prefix is 129.97.24, okay? So I want to refer to all of them, and I want to use my mask notation. How many bits will I have in this mask? How many ones will I have in this mask? Anybody? Yeah, 24, right? Because those are the first, this is 8 bits, it's 8 bits, it's 8 bits, 24 bits. So I call this a network. The jargon, I guess, is that this is a /24 network. Okay, which means that the first 24 bits are common to all the IP addresses in this subnet, in this network. Okay, so in this routing table, to go back to this, if you had a routing table, so let's put some routing table next to it and see what happens. So I have a router over here, and then it has got another subnet, which is 129.97.75.star. In its routing table, it would have entries like this. It would say 129.97.24, running out of space here, .0/24, and let's say this is port 2, this is port 3. And let's say that will be the next port is going to be 2, and then 129.97.24, sorry, .75.0/24, that's port 3. Okay, what does this mean over here? This means that if any IP address that has the first 24 bits as being 129.97.24 arrive over here, I'm going to send it out on that link. If it's going to come with 129.97.75 in the first 24 bits, I'm going to send it down there. Because after that, I don't really care. This router is responsible for figuring it out, how it gets to the end, to the destination. Okay? And this allows us to therefore aggregate. So I don't need this example over here, because that's how I get aggregation. By doing aggregation, what I'm able to therefore do is to refer to big chunks of addresses at one shot. Okay? And that's what you need to do, because there's 4 billion addresses. You can't refer to all 4 billion of them. You're going to have to refer to chunks of them at a time. And this is the chunks that you're going to refer to over here. Yes?
How is that a 24-bit significant?
Okay, why is it 24 bits significant? What I'm saying here is that all of these share the first 24 bits in common, right?
So why is that 24?
Why is it? I just picked it that way. I just chose to be that way.
Okay.
Right? I could have chosen 25 bits in common or something. I just picked 24 because actually 12997 is Waterloo, and we happen to do it this way around here. But there's no reason for us to do it. We could make it a 25 bits in common as well.
No, my question is how can you tell it's 24 bits just like you were doing an 8, that part actually.
Because D is 8 bits.
Here it's 8-bit strings, right?
Okay.
I'm considering 32-bit strings now. I've changed from 8 bits to 32 bits. I see what you mean. Yeah, if I had 8-bit strings, of course, I can't do 24. I can only have up to 8 bits, right? But when I go from 8-bit strings over here, I've now changed. That's a sort of the toy example, and now this is the real thing. This is 32-bit strings, so I can have up to 32. Yeah? Okay, well, I lost you somewhere. Does that make sense?
I just kind of.
You kind of. Do you understand this part here? Do you understand what a mask of 4-bit means? If I have 8-bit strings, what is the longest mask I can have? 8 bits. If I have 32-bit strings, what's the longest mask I can have? 32. So I can have 24-bit masks, right? Which is what I have over here.
So that doesn't make sense.
Yeah. Okay. Yes.
So like the 24, not slash 24, sorry, the 75 then.
Yeah. 75.
Is a number between 0 and 255.
Correct. Yeah. Because if you remember the dotted notation A, B, C, D, each of them is between 0 and 255. It's 8 bits. Right? 8 bits. Yeah. Any other? Yes, over there.
So the AND table.
Yeah.
Right there.
Yeah.
So there's 2 sets of 8-bit strings. Does that mean we have to set 2 sets?
Oh, I'm sorry. So this is the input,
Oh, okay.
and that's the mask, and together we get the output. So we don't have 2 strings. We only have 1 string. This is the string, and then that's a mask, and the mask is written in this form as a /4 because refer to it as a /4.
Okay.
Yeah.
So that one down there makes sense because like you can tell that there's 255 like internal addresses.
Right.
But can you do the example where you had A.B.C.0/30? Because that one seems odd. That
Sure, yeah, that's actually pretty straightforward. Let's say that we actually had a okay, before I get to that, are there any questions about the 24? Because I'll do 30 and then we'll take a break. Okay, yes.
So before that router there,
Yes.
the router before that one would have gotten a /16 request, right?
Possibly. I mean, we don't know. We don't know what's coming before it, but certainly this router needs to distinguish between these two, so we don't know what's before. It depends on how heavily you aggregate, and I was going to actually cover that, but we got lost here. Yes.
All the like the slashes seem to be a difference of 8 with 32.
Typically,
Is that always the
no,
case?
we're going to do a 30 example in just a moment to show you how we can do a /30, for example. Yes, Clarence.
So when you don't have some multiple of 8, then you can't represent it as like 129.97.
Yeah, you can't. It's just kind of confusing, but yes, but it's doable. I'll show you in just a minute. Yeah. And yes.
Would a routing table typically have all the same slash notation?
No, it wouldn't.
No?
No, it would have different ones. Some would have longer, shorter masks. Like the homework question has the 16 and the 24.
And that would be in the same routing table?
In the same routing table, because it depends, I we'll come to that in just a minute. After the break, I'll talk about that. Okay, so everybody okay with this? Because I'll do a 30, and that's a bit, you have to kind of stretch your mind a little bit. But don't worry, it's a break immediately after, so to recover from that. So let me do a 30. I'm going to use this space now, so I'm moving right to left, I guess. So let me talk about a /30. Let me do an example to make it clear what it is. So let's take the following 2 IP addresses. So or the 4 IP addresses. So 129.97.75.0, 129.97.75.1, 129.97.75.2, and 129.97.75.3. Okay? I picked simple numbers. So it can be any contiguous block of 4 that are aligned. So it can be 0 to 3, 4 to 7, 8 through 11, etc. But I just picked this because of the way it's easier this way. So I have 4 addresses. Just 4 any old addresses, and I want to refer to all of them using only one thing, right? Only one thing. How do I represent it? The way I represent it is I call all of these 129.97.75.0, okay, /30. 30 means look at the first 30 bits and ignore the last 2 because these will all differ only the last 2 bits. It's going to be 0, 0, 0, 1, 1, 0, 1, 1. Just to make sure you understand, let me ask you the following question. Let's say I have these other 4 strings, which are these. Okay, so let me take these off. Does everybody get this first? It's a slash 30. Okay, let me make it a bit harder. And now I'm going to make it 4, 5, 6, 7. What is this going to look like? 12997 75 dot what slash what? Okay. Yeah.
4/30?
That's right. It's 4/30. Why is it 4? Because basically this is going to be 1, 0, 0. Okay. And this is going to be 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? So all of them have 1 in the high order bit, which corresponds to 4, which is what we have over here. And they ignore the last 2 bits. So that's why we get 4/30. So we can refer to all 4 of them, as you pointed out. Good. Good answer. Okay? Yes?
So can you repeat that?
Sure. 4 is 1, 0, 0. Okay? 5 is 1, 0, 1. Okay, I should be more precise. 0, 0, 0, 0, 0, 1, 0, 0. And this, 5 preceding zeros before it, right? And all of them. So it's 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? That's the way we represent these numbers. We want to know what's common to all of them. What's common to all of them is this, everything up to here followed by zeros. Sorry, up to here is common. And after that, it's followed by 0 or 0, 1 or 1, 0, 1, 1. Right? And this one, we call that 4. That's the base. Right? And after that, we don't care. So we represent it in decimal as 4, and then say the last 2 bits we don't care about. This is why I didn't want to do this first because it's confusing, a bit confusing. But it's no different from what I had earlier. Right? If I were to change this once more just to kind of drive this fact in, if I were to say, OK, I want 75.8, 9, 10, 11, that's going to be actually 8/30. Okay. So, right. Okay. So you get the same. Basically, we are sharing these. Yeah. Okay. I think that's correct. Okay. I'm not very good at doing math on the board. I think that's correct. But I mean, it doesn't really matter, okay? At this point, all you need to understand it is /30 refers to 4 addresses together. And that's the way that works. Okay, let me take a break. And then after that, we'll see how we can use this aggregation to do something interesting in the network layer. Okay. All right, yes. I just want to focus on aggregation rather than routing tables. I'll come to routing tables right now. Yeah.
Before the break, you said it's important to understand that that represents 4 addresses.
Right.
How do you just start looking at?
How do you know?
How do you know it's 4 addresses?
32 minus 30 is 2, and 2 to the power 2 is 4, right? So, okay, let me ask you a question. A /5, how many addresses is that? It's 2 to the power 28. Okay, is that your final answer? 27. Yeah, that's 2 to the power 27 addresses. Yeah. Okay. All right. So you just take 32 minus this 2 to the power whatever it is. That's what it is. Okay. All right. So okay. So now we understood aggregation. Hopefully. So what I'm going to do is to use this in an interesting way, and the interesting way is to do routing, because that's the whole point anyway of all this bit munging. And so let me show you how to do that. So I'm going to make an assumption, okay? And the assumption is, I'm going to write it down over here. I'm going to say that, yeah.
I'm getting slightly confused, but the thing that you showed there,
Yeah.
you used 8, 9, 10, 11.
8, 9, 8, so it would be 8, 9, 10, 11, yeah.
Yeah. So once you go to 8, you require like 4
Four.
bits to specify 8.
Yeah, but the 1 is shared between all of them.
Yeah.
First one.
The first one will be shared by, okay, let's take that offline because I'm trying to do that in my head and I might have made a mistake, so don't worry, we can talk about it after class, okay? I don't want to get caught up in that. That's like a rat hole of what is it exactly? And I can never get it straight myself. And I've been doing networking for 24 years, and I can't get it straight. You don't need to get it straight. So it's okay. It's not a problem. Okay. Let's think about the big concepts here. I'm going to make an assumption. The assumption is that all addresses within a subnet are mutually reachable. Means you can get from anyone to everybody else. I'm going to make this assumption, and this is because this is given to me by what's called the link layer, which you're going to study later. So the link layer guarantees to me that all addresses within a subnet are mutually reachable. So I'm going to assume it because I'm going to fix it later. I'm going to take out the assumption later. But for now, I'm going to assume it. What does this mean? Okay, it means that if I give you a set of addresses, okay, which are all sharing a common mask, okay, like a /30 or a /24 or /28, whatever it is, you can assume that they can all get from one to the other somehow. Okay, magically they can get from one to the other. Okay, so in other words, I can take something like this, 129.97.75. /6. I'm just making that up, so maybe that doesn't work. And I can say, okay, everything inside this is reachable somehow. Okay, we don't care how. Okay, just make that assumption. Now what I want to do is to use this fact to build a global routing table. Okay, to get from anywhere to anywhere. Okay, so how do we do this? It turns out to be pretty straightforward, actually. So just to make the representation simple, okay, I'm going to not use the slash and mask and so on. So I'm just going to draw what it looks like. Okay, so here is some subnet, here's some other subnet, here's some other subnet. Okay, and we know that inside it, the network addresses are going to just look like, I'm just going to call this A dot star, B dot star, C dot star. Okay, and there's going to be some router over here. Okay, now, what have I done? Okay, what I've done is I've basically chosen one member of this set, okay, call that the router, and I said if I can get it to this guy here, well, the rest are all reachable because I have, by assumption, all the addresses in the subnet are mutually reachable, right? So if I can get to here, I can get to every one of them. Okay, that makes sense? Okay, all right. Now the next thing I'm going to do is I'm going to put another router over here, like this, okay? And this router is going to say have 3 ports going out, one connected to each of them. It has a routing table. And the table says, let's say it's a port 1, 2, and 3. It says A dot star. If you get an address, A dot star, send it to 1. If it's B dot star, send it to 2. If it's C dot star, send it to 3. Okay, that we've already sort of seen, so we can do that. Okay. Now, let's say that I have what I have to do now, what I need to do now, is to see if I can additionally aggregate these 3 guys up some more. Okay, if it's possible to refer to all of them somehow, right? If I've done my address allocation properly, okay, these addresses will also have something in common. Okay, these also have something in common. Okay, and to explain this, if we let's say if I have let's say this was 129.97.24 star. This was 129.97.75 star. This 129.97.36 star. Okay, let's say these are numbers. Then what I could do is that these 3 guys have 129.97 star in common. Okay, using that example over there, right? I've arranged it so that I've taken some chunk, and these are actually smaller chunks I've allocated contiguously. So I take a contiguous chunk, and I take a smaller contiguous chunk, and I hand it off to each of these subnets, and that's how I arrange it. Now, what happens is that some other router elsewhere, somewhere over here, it just needs to have one entry over here. Let's say it goes here, and this one is like that, and this one is, let's similarly arrange to be something like 128.32 star. This one has one router here, another router here. It says, this router's table says 129.97 star, send it to port 1. If it's 128.32 star, send it to 2. That's the table at this router. So 129.97 is Waterloo. Inside it we have like tens of thousands of addresses, but this router needs only one entry over here. okay, to get there. Yeah.
Should the 1 and 2 be switched? Because it's 1 and 2 9.
Oops. Yeah, it should be. Thank you. 2 and 1. Thank you. Yeah. Yeah. Okay. So this router that's far away needs to only know about the whole network over there. Just one entry for all that network. And guess what? That's all we need. Turns out that's all we need. There are about roughly 80,000 of these entries, networks like these, about 80,000 of them. And we can build routers with 80,000 entries in them. So every router in what's called the core, which is what this looks like, this is all called the core over here. So we'll have a core over here. Every router in the core has got entries for every network, okay? Where all of these together will form one network. So this router actually belongs to two different things, okay? So this is called the core. This line I've drawn over here we'll call a network. And this little thing we call a subnet. And this means that they are parts of the same network. They are chunks allocated from the same network, okay? So let's see how this works in a moment, in a bit of detail. I'm going to assume for now that every router in the core can talk to every other router on one hop. Okay, just going to assume that for now, and I'm going to take that away in just a minute or so. Okay, so let's assume every router can talk to every other router. So every router has 80,000 links coming out of it. Okay, going to every other router, and then I have 80,000 ports. So I just look up the destination in the table, and it says, oh yeah, that belongs to network 129.97. I'm going to put it on the port that corresponds to it. Off it goes to this router. This router says, right, that belongs to this subnet, okay, 129 and 2024, and I'm going to send it here, here, or here. And then this one says, oh, that's mine, it belongs to my subnet, and I can get to it because I know the address, because I have that assumption over there. And then we're done, basically. Okay? So even though you have billions of addresses, we can reduce it down to basically 80,000 or so networks. And once you have 80,000 networks, we can actually make it work. Because you send it to the router responsible for it, that sends it to the subnet, and then inside we do something. Okay. Yes?
On the homework question last time where it was 32-bit or 31-bit addressing,
right?
That would break that assumption, right? Like you couldn't...
yeah, it would be impossible. You'd have very, very large routing tables. Right. That's basically going to happen because you can't aggregate them up. Right? You're going to, everybody gets itty-bitty little chunks. So, yeah, that's what happens. Okay. Any questions about this over here? Now, the only assumption I made over here is that all of these routers are directly connected to each other. Okay? And now I'm going to show you how we can get rid of that. It's actually very easy to get rid of. But before I do that, I want to, assuming everybody is only one hop away, you can see how this works. So I aggregate up once more, and then internally I kind of use one hop routing. Okay, so any questions about this? Yeah.
And in this case, the same routing table would have the same slash notation?
Yeah, that would be like a /16. This would be a /16, and so on. Yeah, now we know what the slash notation means. I'm just using star because it's easier to understand. Yeah. Okay, so how do we get rid of the assumption that everything is directly connected to everything else? I'm going to just show that over here. So again, I'm going to abstract this all out. And I'm going to show you a very, very simple example, and you'll see right away how it works, because it's really straightforward. Let's say that I have a network that looks like this. Okay, it's really simple, where now this represents a router, okay, and these are all routers, and then I'm drawing lines to show you some subnets, but I'm just going to show subnets as just numbers. I'm going to show 1, 2, 3, okay, actually these are actually 6, and that's 7, okay. These are not subnets, these are networks. These are all networks like this, okay, and okay, and this whole thing over here is the core, okay. So this is like a simplified representation of the same exact thing. I'm not showing the subnet structure and all that stuff. I'm just showing you this over here, okay. Now I made the assumption that every router in the core can talk to every other router, and I'll show you in the simple example why that's not needed. Okay, you need something else, but it's not that difficult. Let's call this R1, R2, and R3, just to show you how simple it is, right? These are 3 routers. And what I'm going to do is R1 basically needs to know, okay, if I get a destination that has an, that corresponds to network number 1, who do I send it to, right? Well, I'm not directly connected to 3, but 3 is reachable through 2. 3 is reachable through 2. So all I have to do is to give it to 2, and then 2 knows what to do, right? So at R1's routing table will look like this. This is at R1. It says the destination, and I want the next hop. Okay, and I'll just make it even simpler. If the destination is 4, I want the next hop is R2. The destination is 5, the next hop is R2. Well, we know that, because that's obviously where it is. But moreover, if I have 1, 2, or 3, and then it's R2 as well. In all these cases, I'm going to send it to R2. At R2, we have a table that says that if the destination is if the destination and next hop, so if the destination is 1, 2, or 3, I'm going to send it to R3. And if it's 6 or 7, it's going to send it to R1. Okay. And similarly at R3. So even though they're not directly connected to each other, all they really need to know is to give whom to give it to amongst the neighbors who's closer to the destination, and then they kind of hand it off in that direction. It's like the letter to Ireland. You give it to the one that's closer to Ireland, it gets there eventually. Yeah, Sandra.
Didn't this give you like incredibly large routing tables?
Yes.
Scale it up?
Well, no, we only have 1 entry per network number. We still only have 1 entry per network number, and we have 80,000 networks, so we get 80,000 entries. Yeah, so we don't have very large routing tables. We have longer paths, obviously, but we don't have large tables. Yeah. So we have to somehow figure out how to write these tables. Okay, I mean, I'm showing you a toy example. You can write it by inspection. Just look at it and sort of just say this is what it is. But how do you do it? That's the basis of a routing protocol, which we'll cover 2 lectures from now. Yes.
So this only happens in the network of the cores, right?
Yes, only at the core. Correct, yeah. Okay, so this picture shows us that every endpoint, or every router, or every network can get to every other network, even if the core is not fully connected, by using routing tables like this. Okay, how do we get these routing tables? Okay, we'll get to that. But so I can therefore assume that every router in the core is connected to every other router, which is what I needed to get this to work. So if I come back to this picture over here, this router over here actually doesn't have 80,000 connections to it. It only has whatever 20 or so, maybe 5 or so. And all it needs to know is which of its neighbors is supposed to be the next hop for every one of the destination networks. Sends it to that. That in turn looks at its table and says, oh yeah, I have to send it there. Eventually it's going to show up over here, and this says, sure, it's my network. I better look at my subnet table to figure out which subnetwork router to send it to, and there it is. Yes?
And the R1 table would also have 6 and 7 in it?
Well, you don't need it for yourself. You never need entries for yourself because you know it's yours, right? I mean, by convention, we don't write it for yourself.
So this is a different table.
Beg your pardon? This one here? Yeah, you would say if it's for myself, then what I'm going to do is I'm going to look inside deeper, okay? I'm going to look with a longer net mask because I have entries corresponding to longer net mask. I'll come to that in just a minute over there, how we do that. For the
Oh, no, actually, I was just asking, this is a different table for the one we use, right?
It's the same table, I'm just representing it differently. So by R2, I mean, let's say this is port number 1, this is port number 2, or in this case only has one kind of core port. So all of these correspond to port number 1. So I'm just writing R2, I just mean the port that corresponds to R2. So it's the same idea, the destination and next hop, or the next port. Okay, because locally, packets coming in, I look at it, port this, port that, that's all I do. I mean, the router just is dumb, right? It just has some number of ports, just pushing packets out on different ports.
I mean, it's separate table, right? Because you have a table for your network, and you have a table for routing.
That's correct. And I'm going to talk about that in just a minute, yes, in a little bit more detail. Any other questions before I do that? Does that make sense here?
No, 6 and 7, they would also have a routing. Like,
Internally, yes. I'm drawing these big subnets as just these blobs over here. But internally, it would have the same structure exactly like this. Yeah, 6 and 7 would have these kinds of subnets and structure like that as well.
So I
Yeah.
feel like 6 and 7 wouldn't be in that table.
Why are they not in this table over here? I can write them down. I mean, you can just say 6 and 7, it's R1, it's myself, you know, so I could certainly do that. I kind of ran out of space, but I can put that up here. So if it's 6 or 7, it's R1, it's R1. This is a table at R1, right? So, I mean, it doesn't really add in much information. Okay. Okay. But let me clarify that in just a minute. I was going to do it on the other side, so hold on to the thought. Are there any other questions about this over here? Okay, so let me exactly handle that point over here. Let's take a look more carefully at this guy's routing table over here and remove this ABC business, and let me actually use some. So let's say it has 4 ports, 1, 2, 3, 4. Okay, and we'll look at this pretty carefully now. Okay, and let's say there's a link over here, which is link 5, and it goes to 128.32 star, and this router over here. Sorry, let's say it's responsible for 128.16 dot star. Okay, just let's work with these numbers for a moment. Okay. Now, what we want is something like this. We want this router, when it gets a packet, to either send it over here, or to one of its subnets. Okay, which are these subnets: 129, 24, 75, and 36. Correct? So the way we do it is like this. It's actually much simpler than you would think. First of all, if a packet comes from anywhere, it doesn't matter where it's coming from. If it's coming from anywhere and the destination is 129.97.24 star, that should go on port number 1. Right? If it comes to its destination 129.97.75 star, that should go to port number 2. If it needs going to 129.97.36 star, that's going to port number 3. And then these two guys over here, if it's going to 128.32 star, that's going to go to port number 5. And then 128.16 star, it's going to go to port number 4. That's the table. Okay? And as you can see, these guys are going to be /24s, and these are going to be /16. And so this table R, it kind of doesn't have entries for itself. That's why I was saying it doesn't have entries for itself. What it really has are longer subnet numbers, longer masks corresponding to the subnets inside it. Okay, we don't really need an entry for itself, right? There's no entry for itself per se. These are just these ports connected to subnets like that.
Isn't that what 6 and 7 are?
That's right, they are. So 6 and 7 exactly correspond to this. So 6 and 7 well, these are two different networks connected to the same router. Okay, this could be Guelph and Waterloo connected to some router at Orion, for example. Okay, I'm just viewing these as separate networks which happen to share the same router. So for example, just to be more careful, it could be that this router is part of Waterloo's, but I could have some other router like this, which is sitting here, which has got connection here, and it's got connection down there to Guelph and to Waterloo, and then that would only have 2 entries, which are corresponding to quote-unquote 6 and 7, and then this would be what would be 6. So we can arrange it a number of different ways. The theory is still the same. Okay. Any other questions? Yeah. What's the difference between these ones over here?
No, you said it doesn't have
These are port numbers. This is a port number on the router. So you have a box which has some slots connected to it. These are the port numbers. These are the slots over here. Here I'm referring to networks. So this is, if you want, I can call it N6, network 6, network 7, network 5, just to make, okay, these are not port numbers. I'm using a slightly different terminology here. So I'm saying network 6, network 7. There you go. So you should have a, yeah.
Isn't having 1, 2, 3 in there also referring to itself?
Say that again?
Having 1, 2, 3.
These are port, yeah.
Isn't that referring it to?
These are saying, oh, okay, these are actual physical ports. These are actual, if you have a hub at home, if you have seen the network hub, it's like a box with little slots in it. Each slot is numbered, okay, 0, 1, 2, 3, and so on. These are actually the box, the holes, these are the slots corresponding to the router. It's called a port, right? So these are the actual port numbers.
So what do you mean by not having entries for itself?
What I mean is that the router itself is not consuming any data, right? We only know what port to send it out to, right? The router is not a destination. It's just the intermediate point. It's like postmen never get mail. They're just carrying mail for people, right? So we never have an entry for yourself. It just says who does it go to. Yes?
So like if the DST for that router you got was 129.97.star, you wouldn't include it in the table because that's it.
Yeah, it doesn't mean anything, right? 129.97 star. Well, no destination can be star. It will be actually, any destination is an actual number, right? 129.97 or 3.4 or something like that. You cannot put star in a header. The header is just zeros and ones. There's no stars. This is a rule that we use to match destinations with entries in the table. So you're saying we take the header, we ignore the last 16 bits, and then we match it. And if it matches, then we send it to 1. That's what we're saying. Yes?
So, sorry, just trying to make sure I'm clear on this.
Sure, sure.
So for the routing table for core, so that means it has like 80,000 entries plus the number of ports within its own network.
Correct, yes, yes. There are some routers inside the core that only connect to other core routers, right? When you did your trace routes, right, you found many of these with very long, funny, complicated names belonging to Verizon and Cogent and things like that. Those are core routers that talk to other core routers. They don't talk to any edges at all.
Yeah, so in that case, its own network number is going to be 0, right?
That's right. Yeah, it doesn't have any network of its own, correct, yeah. You had a question, yeah?
So for that example on the left, the next things really should be ports.
They really should be ports, and I'm regretting my use of this notation. You know, Emerson said a foolish consistency is a hobgoblin of little minds, but a lack of consistency is a hobgoblin of teaching networking in classes. So I'm going to use port numbers. So this is port P1, port P2, port P3, and then at R1, if it's N6, it's going to be on port P3, and if it's N7, it's port P2. Otherwise, it's all P1, 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 P1. There you go. So it's all port numbers. Okay, let's not confuse things further than they already are. Actually, they aren't confused. I think they're quite clear in my mind, anyway. Okay. Any other questions about this? So let me back up a little bit and just say that, I've thrown a lot of different things at you, but the reason I'm doing it is because I hope you're now getting an appreciation of what IP addresses are, okay? And you're getting hopefully a good understanding of what's actually going on. What's actually going on is that we're doing address allocation geographically. We are not just allocating addresses just as we wish. We have to allocate them in a way which allows us to do aggregation. Once you got aggregation, we can use masks to refer to big chunks of addresses with just one entry, which is what we're doing over here. Okay, we're referring to, in this case, 2 to the power 16, 65,000 addresses with just one entry, which is great. But we need to be able to do that. We have to do it over here. That allows us to construct what's essentially amounts to a hierarchical routing structure. Okay, so we have a single sort of route, and then we have paths that go like so. You go down here. And there's no other way to get there. You have to go through here, okay? And that's actually what we do today. All traffic in and out of University of Waterloo goes to the Waterloo main router, which is in the basement of this building, right? Okay. So basement of this building, this is big box. That's the Waterloo router. Every single packet goes through that router, in a route. It's got to go through that. I mean, of course, your packets inside the subnet and so on, talking about all internal and external traffic goes through exactly one box, okay? And that's the way we built it like this. Just a minute, Tom. Inside the core, we have a structure which is a mesh. You can have multiple paths and so on. This one doesn't have to be only one path. For example, this can get there either this way or this way. Right? If you've seen over here, I've drawn a triangle. And later on, we'll see how this makes a decision, because it could get there one of two different ways. It has to choose, quote unquote, the shortest path. This is no more complicated than by saying I can get home from here to home. I can take this road or that road. I've got to choose the best road. Okay, that's a routing problem. We'll get to that. But from our perspective, what this router has in the core is that for every single network, it has what's the next port to get to. It's a really dumb table. Take a destination address, mask off the bits, look at what's left, compare it with over here, And then we have this rule that says, look at the longest prefix, right? Because we want to sort of compare the longest number of bits possible, and we do the longest prefix match, and then we look up where it goes. Okay, and so that would be the hint to look at this over here. Okay, we want to match the longest possible thing that you have. And this now allows us to scale. We can build a network with a billion endpoints or 10 billion endpoints, and it still pretty much scales. Okay, any questions about this over here? Okay, so that was this thing on networks and subnets. Let me take another. But actually, I kind of snuck in a lot of routing. So when we come to routing, it will be very easy to understand routing principles. I kind of covered routing principles. The thing is, the subject is not like this one little silo here and something here, and you can kind of go one chunk at a time. It's all, it's a network. It's all mixed together. And to understand each piece, you have to understand all of it. And I'm trying to present it in a way which makes sense, and so it doesn't necessarily follow the way I'd like to present it, but that's okay. Okay, let me see. I want to briefly talk about datagrams and virtual circuits, and then get into the IP header finally. Today, by and large, the internet uses datagrams. So what are datagrams? Datagrams are basically nothing but postcards. Okay. It's like postcards. You take a letter, you pick a postcard, you write, hi, how are you, whatever. You put your stamp in it, and then you put your address over here. And you put it into the postal network, and it makes its way to the destination. It doesn't matter how it gets a destination, but basically it gets there. And most importantly, let's say your datagram, your postcard, gets lost somewhere and shows up in some part of the world accidentally. It gets teleported to some part of the world. Doesn't matter. It'll still get to the destination. Everybody knows what to do with it, right? So everything you need to know about how to tackle it, how to deliver it, is contained in the datagram itself, in the destination address. That's a datagram network. There's another way of doing it called virtual circuits, and I'll explain how that works using a simple example. Okay, and the virtual circuits looks like this. It's like how phone calls are made. So I'm going to explain how that works like this. Okay, so I have over here, I'm going to use circles to represent routers like this. Okay, so the way we do it is like this. So we have 3 routers in this example over here, and we have some source. And there's some destination over here. Okay, we want to achieve 2 goals. Okay, let's say that there's actually multiple ways of going from the source to destination. We want to achieve 2 goals. We want to use exactly one particular path for all communication between the source and the destination. Okay, only that path, no other paths. In other words, you want to pin down the path. Okay, you can't use an alternate path. Okay, the first goal. So we want to pin paths. And the second thing we want to do is we want to use short addresses. Instead of the whole, I want to use very, very short addresses. Why do you want to use short addresses? Because I can use smaller headers, and then the lookup is faster, and so on. So it makes your router very, very small and fast and cheap if you use short addresses, because you don't need to look at, let's say, 32 bits and look at this big table. You just want to do something small. How do we do it? We do it in 2 steps. The first, we send a postcard. We send a datagram. So step 1, we set up a datagram along some path. Okay. And then what are we doing exactly? So let me use my colored chalk over here. So let's say that the datagram follows this path to go from the source to the destination. Okay? So what I mean to send a datagram, I'm going to put the full destination address. Okay, please send it to the destination. And I'm going to send it to the first router along the path. Please send it. and then this router is going to do something, and then it's going to eventually get there. Okay, what is it going to do? What the router is going to do is it sends back a message like this saying use some number. So green is a message, and let's say it says use number 1 when you want to talk to this destination. Just use 1. Okay, whenever you want to talk to destination, just use 1. And let's say that the port number, if you remember we have port numbers here, I'm going to number these port numbers in yellow. So I have 1, 2, 3. Okay, I'm going to set up a table at that router over here. So this is what the table looks like. It says if the destination, and this is the port, same kind of idea as before, if the destination says 1, send it on port number 3. Okay? So destination is 1, send it on port number 3. That's all I'm going to do. Right? I don't need to know the full destination address, right? And now this second router, similarly, it has 1, 2, 3, 4 as its ports. And this is ports 1 and 2. The yellow refers to port numbers, okay? So this one said use 1. What does use 1 mean? Use 1 says, whenever you want to talk to this destination, whatever the destination is, just tell me 1. That's all I need to know, and I know that I should send it on port number 3, okay? The next step, what happens is that this router is going to send the same datagram onwards to this guy over here, and this guy is going to say, hey, you know what? I'm already using 1 for somebody else. Okay, I'm saying use 2, for example. Okay? That means if you want to get to this destination over there, just make sure that you're sending on the header the number 2. Okay? So what does it do? That this table actually has got one more entry in it. Okay? And the next label. And the next label is going to be, in this case, 2. Okay, so that's all I really need to tell you. Let's walk through this step by step, okay? So the source over here, and I'm getting a bit cramped, so let me draw a line here too. Okay, the source over here, it wants to talk to this destination, and it puts the full address over here, so everybody knows what it is. And it gives it to the first router over here, okay? This router says, okay, this destination, I'm just going to refer to it as destination number 1. So whenever you want to send anything to destination, use 1. So that's that message over there. It forwards this to this guy over here, and this one sends back to this router a message saying, okay, for this destination, you know, from whatever source it is, just use 2, okay, to refer to it, okay? And then this allows this guy over here to set up a table that says, if anything comes to me on some, that with the destination 1, I'm going to send it on port number 3, means send it over here, and I'm going to swap the label. I'm going to call, instead of calling it 1, I'm going to call it 2, because this guy wants me to call it 2. Okay, and we call this label switching, right? And switching the label and the header. And we repeat this. So when this message goes here, this guy sends a message here saying, okay, use something. And this routing table is going to say, okay, when I get something that looks like 2 as a destination, I'm going to change it to calling it, let's say 7. And I'm going to put it on this port number. And I'm going to do this and so on. So step by step, we are kind of setting up this path. And as you can see, once we send any packets, it's pinned down. Nobody else can do it. No other path can be used because it has got to follow this path. Because I'm stating what port number it goes on. And we use very short addresses because once this thing is set up, we only need to put this one number like 1 or 5 or whatever, a small number, rather than the entire destination address, which is 32 bits. We can typically restrict it to about 16 bits or 10 bits or something like that, okay, depending on how large your network is. So and the lookup is very, very straight. We don't need to do this longest match and things like that, right? We just take the number, look up the table, and off it goes. And we can therefore build very, very cheap, fast routers. Okay? And so this technology is called virtual circuit technology. It was proposed back in 1969, actually. And a number of different networks used it. The biggest use of it came to a technology called ATM, which stands for asynchronous transfer mode. Don't worry about it, why it's called asynchronous and so on. So ATM was a big network technology of the mid-90s. The current meaning of ATM is another terrible mistake. Okay, and So there's a big fight between the internet people, the datagram people who are doing IP, and the internet, the ATM people who are doing virtual circuits, and basically IP won. Okay, so ATM got wiped out. It still resides in bits and pieces. So your DSL line, for example, uses ATM, and there's something called MPLS, multi-protocol label switching, which is exactly this, which is ATM as well. So in fact, it's using the label switching idea over here. Okay. Yes?
So just to try to make things clear again.
Sure.
So the use one means, the one means the short address, right?
The one means that when you want to send a destination, when you want to send a packet to that destination, put one on the header, and I'll know that it means that you want to send it to a destination over here.
Is there a short address?
That's short address. Yes, correct. Yeah, I'm sorry. Yeah, that's right. That's a short.
Each router has the different label of short addresses.
That's correct. It has a pool. Yeah, it has a pool of addresses, and it just allocates it. And so this initial green thing is called the call setup, and then after that we have the data transfer. So just like when you dial the number on the phone, that's doing call setup. Once that call is set up, all packets from source to destination follow exactly the same path. So it's exactly the idea over here. And then we are going to do this label switching. We have to switch labels because maybe that one is already being used. So we have to change the label. So this is what's called label switching. Okay, and it's, but it does allow you to do these two things. You can pin paths and use short addresses. Okay. Any other questions? Yes?
So in that example, there's
Something's going to explode any minute now.
total of four postcards that we can, 4 destinations that we can send it.
Well, I'm just showing you one destination. There are many different possible destinations, right? I could have destinations. I could set up many different paths.
I'm just confused with the numbers.
These are port numbers, right? So I have 4 ports, 1, 2, 3, 4. I have 2 ports. This is a router with 3 ports and so on.
So for example,
This one here.
okay, so that one has port number 2, 3, and 4.
1, 2, 3, and 4. Yeah. There's 4 ports. Yeah.
Okay.
Yeah. Yes.
Is it a coincidence that next label matches up with the port number you use?
It's just a coincidence, yeah. Yeah, it doesn't need to be. Yeah, it could be. I could have said use 25, for example, and then this would be 25. It's just yeah. It's just whatever it tells you to use. Okay, it's like a note. Yeah.
So the changing of the label changes the path it goes through.
No, the path remains pinned down. It's just that the labels keep switching because the label is unavailable to use at the next hop.
It's just a name, so it's just a short address.
Yeah, just a short address that you're using to pass things around.